We're now ready for part one, or step one, of our procedure, which is to determine the total mass of each isotope within our sample of M&Mium. Just as in any sample of a naturally occurring element, there are different isotopes in our sample of M&Mium. We're going to physically sort these different atoms of each isotope into their group. In real life, this sorting is done by a mass spectrometer. And later on in this year, we'll learn a little bit more about mass spectrometry and how it works. For right now, we're going to separate all of our atoms of M&Mium into their individual isotopes. Plain M&Ms, peanut butter M&Ms, and peanut M&Ms. Once we've separated our entire sample into the three different isotopes, we're going to find the total mass of all the atoms of each particular isotope. We'll begin by finding the total mass of our plain M&M isotope. To do this, we're going to take all of the atoms of that particular isotope and find their total mass. The total mass of the plain M&M isotope is 42.92 grams. We're going to repeat this process now for our peanut butter M&M isotope. The total mass of our peanut butter M&M isotope is 10.54 grams. And lastly, the total mass of our peanut M&M isotope is 5.23 grams. All right, we are now ready for step two of the procedure, determine the number of each isotope. Each type of M&M represents a different isotope of the element M&Mium. And it's our job now to count each individual atom of each particular isotope. So we'll start with the plain M&Ms. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48, 50. There are exactly 50 plain M&Ms in this sample. We'll next count the number of peanut butter M&Ms. 2, 4, 6. There are 6 peanut butter M&Ms in this sample. And lastly, we will count the number of peanut M&Ms. There are 2 peanut M&Ms in this sample. In step 3 of your procedure, you will be determining the average mass of an atom of a particular isotope. In this video, I'm going to help you do this for your plain M&Ms. In order to determine the average mass of one plain M&M, we need to take the total mass of our M&Ms and divide it by the total number of M&Ms. In this case, our total mass was 42.92 grams. And our total number of M&Ms, plain M&Ms, was 50. So we're going to take 42.9 grams and divide it by 50. And we will find that our average mass is 0.8584 grams. Now, before we can finish this answer correctly, we need to round it to the correct number of significant figures. Because we are performing division, we can only have as many significant figures in our final answer as the measurement with the least number of significant figures. This measurement has 4 significant figures. This measurement has an infinite number of significant figures. And the reason it does is because we are counting objects. Whenever you are counting objects, like a number of M&Ms, or perhaps like a dozen eggs, or 3 students, that particular number has an infinite number of significant figures because it is infinitely precise. You have exactly 3 students, or a dozen eggs, or in this case, 50 M&Ms. As a result of that, we're going to look to this number to figure out how many significant figures should be present in our answer, which in this case is 4. So I'll count out 1, 2, 3, 4. And I have exactly 4 significant figures in my answer because leading zeros do not ever count as being significant. In step 4 of our procedure, we need to determine the percentage abundance of each isotope present within the total sample. In order to do this, we are going to take the number of atoms of a particular isotope and divide it by the total number of atoms within the sample. Let's complete the calculation for plain M&Ms. As noted in the above problem, we had 50 plain M&Ms. We're going to divide that by our total number of M&Ms within our sample. In this case, our total number was 58. 50 plain M&Ms, 6 peanut butter M&Ms, and 2 peanut M&Ms. $50 divided by 58 is 86.20%. Excuse me, 21%. Because we are doing division, we need to, when we're looking at the number of significant figures in this answer, we are going to make sure that we include enough in our answer so as not to limit calculations later on. Because both of these numbers are counting numbers and are therefore infinitely precise, we're going to pick a number of significant figures to include in our answer, which in this case, we're going to include 4 significant figures. In step 5 of your procedure, you're going to determine the relative abundance of each particular isotope in your sample of M&Mium. The relative abundance is a decimal when added all together should equal close to 1. The percentage abundance refers to a more global sample. The relative abundance is going to refer to our particular sample. So we're going to take our percentage abundance and divide it by 100. In the case of plain M&Ms, that's going to be 86.21% divided by 100 is going to equal 0.8621. And again, that is for plain M&Ms. In step number 6 of the procedure, you will be determining the relative weight of each particular isotope. In order to do this, you're going to take the relative abundance of the isotope and then multiply it by the total the average mass of that particular isotope. So let's see our calculation for plain M&Ms. We're going to take our relative abundance and we're going to multiply that by our average mass. And we'll find that our relative weight sorry about that. Is equal to 0.7400 grams. We have 4 significant figures here. We have 4 significant figures here. So we need to make sure that we include 4 significant figures in our relative weight. Once you've calculated the relative weight for the other 2 isotopes, then you will be ready to determine the average atomic mass of the element M&Mium in step 7 of your procedure. We're going to zero our balance, and then we're going to gather all of our plain M&Ms and take their mass. The mass of our plain M&Ms is 42.05 grams.